Okay, so recap. What we proved last week that if G is a three-connected graph with no Kiritowskis subgraph, then contracting an edge does not produce a graph with a Kiritowskis subgraph. We also showed that if you take a three-connected graph, somewhere you're going to be able to find an edge within that graph such that the contraction of that edge is going to the contraction of that edge is going to produce a graph that is still going to be three connected. So now remember also we chose a graph G to be the smallest graph that has no Kiritowskis subgraph that is non-planar, and we want to obtain a contradiction. We chose this graph to be the smallest possible graph. We proved that this graph is we proved that it has to be three connected. Right, so now what we're going to do is we want to take the graph G and make it even smaller. And we're going to make it smaller by contracting an edge. Now remember, the choice of G means that if I make G smaller, then the resulting graph, if it doesn't have a Kiritowskis subgraph, the smaller graph is going to be planar. So then using the fact that the smaller graph is planar, we're going to retract the edge again and get that G has to be planar. But we're going to prove it. We're going to prove a different result for three connected graphs, which is going to imply planarity. So we'll get to that just now. Okay, so remember now we prove this. If G is a graph which is the smallest counterexample that doesn't have a Kiritowskis subgraph, we proved now that this graph is three connected. And now we just need to show that we have to show that every three connected graph without a Kiritowskis subgraph is planar. Remember now we assume that G is non-planar, so we want to get a contradiction that way. Then we already proved lemma A and lemma B. Again, what is lemma A? If G is a three-connected graph with order at least 5, then there exists an edge whose contraction results in a three-connected graph. Remember, I said you can somewhere find an edge that you can contract without it affecting the three-connectedness property. Then lemma B as well, which is the other one I mentioned. If G is a graph with no Kiritowskis subgraph, then contracting an edge does not result in a Kiritowskis subgraph. Right, so having that out of the way, we introduce what is known as a convex polygon. So what is a convex polygon? And this is necessary for us. We say a polygon is convex if no line segment between two of its vertices intersect the outside of the polygon. Right. Equivalently, that's the same as saying that every interior angle of a convex polygon is smaller than pi. Right, so there you can see that line segment there. It joins two vertices, and that line segment intersects the outside of that polygon, so that's not convex. And this here is an example of a convex polygon. You can take any line segment joining two vertices that will always intersect the interior of the face. Right, now having discussed that, we also just need to check what a convex embedding is. We say a convex embedding of a planar graph G is a plane graph G with all the edges being straight line segments, and in which the boundary of every face is convex. So we now investigate which planar graphs have a convex embedding. So again, this is just an example here. So here you've got a situation where you don't have that convex property. You can join those two lines and you'll see that that line intersects the outside of that region there. So that's clearly not convex. here, and you can go and redraw that here and, in that way. You'll clearly see that that's convex. All the faces pretty much have that convex property, and they're all straight line segments. Right, so basically convex embeddings and connectivity. Now this example here, if you look at K24, right? Now it happens that K24 does not have a convex embedding. So not all planar graphs have convex embeddings. But if you go and investigate the connectivity of K24, you can clearly see that its connectivity there is 2. So basically, you will see now that when a graph is 3 connected, a planar graph is 3 connected, then it's a different story. So that's why they say here, on the other hand, we show that for 3 connected graphs, this is not necessarily the case. So that brings us to the following theorem. So we want to prove Kiritowskis theorem. So this theorem says if G is a 3 connected graph and it contains no Kiritowskis subgraph, then it happens that G has a convex embedding with no 3 vertices on a line. Okay, so now what we want to do is we want to prove, if we can prove this theorem, then for G that we chose to be our smallest counterexample, that is 3 connected, doesn't have Kiritowskis subgraph. If we can prove this theorem, then that smallest counterexample we chose, which is G, is going to give us a problem, because according to this theorem it will have a convex embedding, and therefore it will contradict the non-planarity, because if the graph has a convex embedding, then automatically it is going to be planar, right? So that will imply that G is planar, and that will complete the proof of Kiritowskis theorem. So we're going to use induction, or you can prove it also by a smallest counterexample. You can choose G, 3 connected graph, to be the smallest graph with no Kiritowskis subgraph, that doesn't have a convex embedding. And then you're going to make that G smaller and then get a contradiction with the fact that the graph has doesn't have a Kiritowskis subgraph. Or you can prove it by induction. So remember, now we're going to use the contraction of the edge to make my graph reduce the number of vertices of the graph. So that is how this proof works. So they prove that claim by induction on the order of G. So we take our graph G to be 3 connected. We assume it doesn't contain a Kiritowskis subgraph, and now we want to prove that it has a convex embedding. All right. So we start with our base case. We start with order at least 4. So if you look at a graph of order 4 that is 3 connected and doesn't have a Kiritowskis subgraph, then the only one that you basically get is this graph here, and it is clear that that graph has a convex embedding. Right, so the induction step works now as follows. So we're going to take now our graph G, which is 3 connected, and we know by our previous lemmas we can find an edge somewhere that we can contract, and that will lead to a new graph, G subscript E, and that graph will definitely still be 3 connected, right? Now also this new graph that we constructed by contracting an edge, it will also have no Kiritowskis subgraph, so we can apply the induction assumption. So this graph is this new graph, G subscript E, is going to have a convex embedding. So again, by the induction hypothesis, there is a convex embedding of G with no 3 points on a line. So now we know this, and now what we're going to do is we're going to retract the edge eventually and get a problem for the graph G. Right, so what they do is let Z be the vertex of GE obtained by contracting this particular edge E. We know that since G subscript E is 3 connected, we know that removing Z results in a face F with a boundary that's a polygon. Right, so why is this the case? Let's just go and check this out, what happens. Okay, so there's my vertex Z, and so these are all regions, right? So those are all possible regions. Okay, region 4, that's just a specific example where Z has degree 4. Z can have any degree, can pretty much have any possible degree. Alright, so Z can have any degree at least 3. Remember, because the resulting graph is still going to be 3 connected, and a 3 connected graph must have, every vertex must have degree at least 3. Right, so those are all regions, okay? Okay, so there's representation. Now these regions, what would happen if two of these regions, or if two or more of these regions are the same, and they are all the exterior regions? Right, so then you've got this situation here where let's say region 1 and region 4 are both the exterior region. Then you're going to have a problem, because then what's going to happen if I delete Z? If I delete Z, then my graph is going to become disconnected. And that is going to contradict the fact that my graph is G subscript E is going to be 3 connected, right? So deleting Z. So I mean, you cannot have more than one of those regions. You cannot have more than one of those regions being equal to the exterior region. So at most, one of those regions can be the exterior region. Alright, so let's say region 1 is the exterior region. Then you have that situation, and you can actually see Z is inside a polygon. So your polygon is basically that whole thing there. Okay, so there's your the inside of the polygon, and the inside is this whole basically area. If you go and delete Z, right? So deleting Z, there's your polygon, right? So it's basically this. It's in that whole area there. Right, so if none of those regions is the exterior region, then you have this situation here, and if you go and delete Z, then you get that situation there, and again, your polygon is going to be this region. Okay, so this is going to be a new face, which is all the faces R1, R2 up until R4 merged together. Now, since GE is 2 connected, the boundary of F is going to be connected, as I've explained. And so we can go and delete this vertex Z. So this vertex Z there, it lies inside of the face of this new polygon. And remember now that the edge that I contracted is the edge XY. So that is the edge that I contracted there. So note that X and Y, they share. If I take the edges incident with Y and the edges incident with X, as I merge X and Y together, those incident edges are going to become the edges incident with the new vertex Z. So if I retract it again, my neighbors of y and my neighbors of x are still going to be inside of this polygon. Okay, so I don't have any edges of x and y, say, that go outside of that polygon. They are going to stay nicely inside the boundary of that polygon. So now I just need to look at a few cases. I need to see what happens in those cases. Right, so now what they do is they just take the vertices of this of the polygon in which these vertex Z lies, and they just label the vertices x1 up until xk, and they are all the neighbors of x arranged in a cyclic order according to their position on this face that we talked about, which is this whole face here. Okay, right, so going back to this sketch here, the neighbors I'm talking about, those are the neighbors, and sorry, not that one. Those are the neighbors of x. Right, so again, just an illustration there. So now we've got this that region that we talked about, which is the inside of that new face, and the red edge is the edge that you've contracted, and now you basically go and label the neighbors of x on that face, right? So that those will all be all those neighbors. We label them in a cyclic order, just to make it easier. All right, so they look at now at the first case. If every neighbor of y is between xi and xi plus 1, possibly including the ith and the ith plus 1 x, then we can expand E back and obtain a convex embedding of G. So what does this look like? Alright, so there we've got the neighbors of y, and they lie between xi and xi plus 1. We're contracting the edge xy into z. Now y can share the neighbors xi plus 1 or possibly xi with x. Right, so we apply the induction assumption then on the resulting graph, and then we just retract the edge xy again to get to my original graph G, and that convex embedding is going to be a convex embedding of the graph G, and therefore we are done with that particular case. Right, so we've looked at the case where the vertex y, all of its neighbors lie between xi and xi plus 1. They could possibly include xi and xi plus 1. So the only two cases that we have to look at are the following two cases, which I'll discuss just now. Let's look at the other possibilities first. Right, so going back to our sketch, the one other possibility is where, alright, y could have some neighbors between xi and xi plus 1, and it also has a neighbor on the boundary of this face that lies outside of this particular region, right? Now x, as an example, x could possibly be adjacent to this vertex or not. We can have that possibility, or we could have that possibility. Okay, so there, just look at the contraction. So there we again contracting the red edge. We are contracting x into y to get the vertex z. So doing all that together, you can then see what the vertex Z looks like in that case. And again there we've got, we retract the edge back to go from G subscript E to the graph G. Now you'll see that retracting that back again, you see we're getting a crossing there, so we need to now somehow show that there's a subdivision of K5 or K33. Right, so go back there to the sketch and let's label our vertices. Okay, so let's partition the B's and the A's in two different sets. So there we've got the B's. Right, and grouping the A's together there as well. So there we've got the A's. Right, now note that A1 is adjacent to B2 and B1, right? So A1 is adjacent to B1 and B2, and in terms of B3, we can take the path on this face that I'm talking about that runs all the way there and goes through here to B3. So essentially that is a subdivided edge, okay? Then if we look at A2, A2 is adjacent to B2, it's adjacent to B1, and it's adjacent to B3. A3 is adjacent to B1, it's adjacent to B2, and again there's a path from A3 to B3. So that is another subdivided edge. Right, so again, if we look at B1, B1 is adjacent to A1, it's adjacent to A3, and it's adjacent to A2. B2 is adjacent to A3, it's adjacent to A1, and it's adjacent to A2. B3 is adjacent to A2, again it's got this path here, and it has that path there. Right, so essentially what have we got here? We have a K33 where two of the edges have been subdivided multiple times, and essentially we have this. So A3 is adjacent. Well, you can just look at it this way. There we've got a we just connected to see the pattern here. There we've got that, there we've got that, and again A1, there's B adjacent there, it's adjacent there, and just draw that edge there, okay, and then B1 is, you know, you can have that edge there. B2, there we've got that edge there, and B2 is also adjacent to, we have those three edges there, and then B3 again adjacent there, and we've got that edge there. So that there is a K33. That's a K33, and the subdivided edges of the K33 is that edge there. So it's that edge there, and the subdivided edge is that edge there. Right, so you can easily see that's a subdivision of K33. Okay, so we essentially looked at this case here, and it produces a contradiction, because then we get that G has a subdivision of K33. So the only other possibility that exists Right, so this vertex y, it cannot have like a neighbor, say, that lies somewhere there. Okay, so if it has a neighbor that lies between two neighbors of x, then it cannot have a neighbor that lies somewhere there, right? So that can't happen. Right, so we look now at the case where y does have a neighbor between two different neighbors of x. So we may assume that y pretty much has only common neighbors with x on the boundary of that face. So so let's consider those cases. Right, looking at that case, that's the case where y has 3 or more common neighbors with x. So we already looked at the case where y has a neighbor that lies in between two neighbors of x. Right, and in this particular case, again, on closer inspection, if we look at right, so if we look at the following, so basically you can see it in this way, right? So right, so looking at those 5 vertices, you can then go and see that like joining that there, that vertex there, that vertex there, that vertex there, right, that vertex there, that one there, that one there, that one there. So we're having 4 edges between each one of these vertices. Okay, so there we've got that edge there, and yeah, so that pretty much takes care of that. Right, and we join y with that edge there and that edge there. So that brown, the blue section with the brown edges, that's a K5. And what we're going to do now is you can go and delete that edge there, and you can go and replace it with that path there. Okay, you can then go and delete that edge there and replace it with that path there, and you can go and delete that edge there and replace it with that path there. And you can immediately see that is a subdivision of K5. We've taken 3 edges from that K5 and we've pretty much replaced it with a path, and that's equivalent to just subdividing 3 edges numerous times. Right, in the case where, say, it has 2 common neighbors, I mean that when it has the neighbor there, we already established that case. That is clearly a convex embedding for G. Or it could have a, say, what happens if that happens, say. Well, I mean, that again is a variation of the case we just looked at, and that you can just go and redraw as. Okay, so that boils down to just the previous case. So we can redraw it in that way, and it is clearly a convex embedding of G. Alright, so basically that takes care of that case. Okay, so therefore we've proved now that that the graph G has a convex embedding, and therefore it has to be planar, which is a contradiction because we said G is not planar. So that proves Kiritowskis theorem. So every graph that doesn't have a Kiritowski subgraph is going to be planar. So now let's quickly look at some applications of planar graphs. And the concept of a planar graph is related to a very well-known problem in graph theory, which is the four-color problem. Right, just an extra note, Kiritowskis Theorem it just states that any simple planar graph can be drawn without crossings so that each edges are straight line segments. So we're not going to do the proof of that theorem. Okay, so basically we can now go and apply that, and remember what a map coloring is, right? So here you've got basically a map of the US with all the states, and now the question is, can we color each face with one of three colors so that no two adjacent faces have the same color? That's a question. So that brings us to the actual statement of the four-color problem. The question is, the theorem states, in fact, that every map has a four coloring. And again, some history, this problem was asked quite a while ago, 150 years ago, and they did prove this theorem. However, a large portion of this proof relied on excessive case analysis, and for that they used computers to analyze the cases. Right, so a portion of this proof is they used computers to do this. So there's a debate on whether it's actually a proof computer proof is actually a valid proof. You know, like some mathematicians feel it isn't. Others feel there's nothing wrong with using computers. Like only in exceptional cases it becomes necessary, but the ideal is to actually have a handwritten proof as opposed to a computer proof. So now, so I mean, I need I can get away with four colors. I can color the faces of a map in such a way that no adjacent regions have the same color, and I can get away with four colors. So basically this problem is a planar graph problem, because what you do is you place a vertex in each face of the map, and then you join two vertices when two regions are adjacent to one another. So you can clearly see here, right, this whole thing here is, if you take the graph away, that's a map, and again you place a vertex in each face, and again there we join those two vertices there because the faces that they are in are adjacent, and so that is how you form the edges of this particular graph. Now this graph that you get is a planar graph, right? So now the question, you can translate the four-color problem into coloring planar graphs. How many colors can you get away with? Okay, so maps and planar graphs. So we're going to approach this problem by using graphs. So a graph that is obtained from a map is planar. So again, you take the map, you place a vertex within each face of the map, you join two vertices when the faces that they are in are adjacent, in the sense that they share a border. Also similarly, you can also reduce the problem of the coloring of a planar graph G to a problem of coloring the faces of a map. And you do that so you go from graphs to a map, and you do that by coloring the vertices of G, or coloring the vertices of G is equivalent to coloring the faces of the diel of a graph. The diel of a graph is basically a representation of a map, of the map that you get from the graph. So you can go from a map to a graph, and then from a graph to a map. Right, so coloring planar graphs. So since coloring of planar graphs and coloring maps are equivalent problems, the four-color theorem implies that every planar graph can be colored with four colors. Right, and we won't prove the four-color problem. We'll go up until 5 colors. And it's too complicated for us to do in this course. Right, so the 4-color problem says you can get away with 4. So that brings us to this following theorem. Well, we can make it easy at first and see if we can get away with 6 colors. Can we quickly prove that? So here they ask us to prove that any planar graph can be colored by using 6 colors. So again, remember the 4-color problem can be modeled with a planar graph. Remember, how do we construct this planar graph? We placed a vertex in each face. We join 2 vertices when the faces that they are in are adjacent. And when are 2 faces adjacent? Well, when they share a border. Okay, so now we basically just need to look at planar graphs. How they do this is, recall a planar graph has at most 3 n minus 6 edges. So you can prove this by induction. So what you do is, since the number of edges of a planar graph is at most 3 times its order minus 6, you can go and calculate the average degree of that graph. Remember that twice the number of edges of a graph is the sum over the degree sequences. So how do we get the average degree? Is we take the degree of each vertex, we add it all together, and we divide it by the total number of vertices. And again, that is just pretty much that term there. And that, according to this formula there, or inequality there, is at most 6 minus 12 over the order of V. So basically, by the law of averages, there will be a vertex somewhere in the graph that must have a degree smaller than 6, according to this inequality. If that weren't the case, this inequality would immediately switch around. Okay, so now what we do is we pick a vertex V that is smaller than degree 6, right, and we remove this vertex V. The resulting graph will be still a planar graph, and according to my induction assumption, I will be able to color it with 6 colors. And now we can just pretty much take V and place it back. We have 6 colors at our disposal. Now, because V has degree smaller than 6, it's got at most 5 neighbors. And each one of these 5 neighbors could possibly be colored by a different color. So we can just pick a color that we haven't used in the open neighborhood of V, and color V that color, and get a coloring that has got 6 colors. Right, having done 6 colors, what about 5 colors? So we're going to prove that any planar graph can be colored by using 5 colors. So again, we again start the proof in the same way. We employ induction on the number of vertices. So again, by the previous result argument, you're going to find a vertex V that has got degree smaller than 6. Right, so you take this vertex and you delete V to obtain the graph G1, and then by the induction hypothesis we can get away with 5 colors. So again we place V back, and now we just have to find a suitable coloring. Now if V happens to have a degree at most 4, okay, so there's V, and V's neighbors have already been covered in the larger graph. Right now we have 5 colors at our disposal. We've already hypothetically used up 4 of them, so we can then go and color a V with any color other than the ones that have already been used. Alright, so let's pick a color. We can color V with red. Okay, so my graph is going to have a coloring where I've used 5 colors. So that is the case where V has smaller degree than degree 4. It works exactly the same. So now we just need to, we know the graph has a vertex of degree smaller than 6, so we just have to look at the case where V has degree 5. Okay, so that takes care of the case where V has degree 4. So what happens if V has degree 5? Okay, so the case where V has degree 5, we can assume that V's neighbors already, V's 5 neighbors have already received different colors. So what do we do now? We consider the case where V is of degree 5 and each of its neighbors is of a different color. Right, so if removing V disconnects G, we can permute the colors in one of the components and obtain a valid coloring. Alright, so there we've got a representation, deleting V if it's disconnected. We look at each component. Remember, we already colored the neighbors of V with fixed colors. Now let's say, hypothetically speaking, I'm recoloring the red vertex, coloring it green, okay, and let's say no problem arises. Then I can pretty much I can go and color V red without having a problem. So coloring that red vertex green was a problem. So that only happens when the red vertex has a green neighbor. Okay, so we can't color that vertex green. So right, so what happens if let's say I color the yellow vertex blue, what happens then? Right, so let's color it blue. If no problem arises, then again we can color V yellow without having a problem. So the problem comes in with that blue, with the yellow vertex that we colored blue. That problem comes in when the yellow vertex has got a blue, say a blue neighbor. So now we do what they say in the notes, you permute the colors of this component. So what you essentially do is the following. You switch the yellow and the blue colors around, and you switch the green and the reds around, only within this particular component, right? So now what you can do is, now you can go and recolor V. You can recolor V as either red or yellow. Right, so there we've got our coloring, which in this case works perfectly fine. Right, so we may assume that deleting V is going to be a connected graph. Right, so we may assume that taking V away is a connected graph. Okay, now if I can somehow color 2 of V's neighbors the same color, then my problem will be solved. So let's focus on, say, yellow and blue. Can I change, can I color the yellow into a a blue. Can I recolor the yellow vertex in this case, which is that vertex there? Can I color it blue? Well, the problem will come in where either there's an edge between that vertex or that vertex, the blue and the yellow vertex, in which case there's an actual path, an alternating yellow and blue path between that yellow vertex and the blue neighbor of V, the yellow and the blue neighbor of V. Okay, so we established that this yellow vertex here, we cannot color that blue. If we can color that vertex blue, right, then we have that situation there, and then we can basically color V yellow, and we have a coloring that works. So therefore, basically this vertex here, we cannot color that blue, so it must have blue neighbors. Right, so that we call this set here now all the blue neighbors of this vertex here. So now if we color all these vertices yellow, we get the following situation. So there we've got a yellow vertex there. We've just colored it from blue to yellow. There we've got a yellow vertex there, and there we've got that yellow vertex there. So again, and then what we need to do is we need to take that vertex and color it blue. Okay, and again, if that doesn't cause a problem, you can go and color the yellow, and so we've got our desired coloring. Right, so going back again, so this set here, we cannot color all of it yellow because there will, some of these vertices in here will have yellow neighbors. Right, so again, take this set here to be all the yellow neighbors of all the vertices in that set there. Right, and we can keep on generating these sets. And because the graph is finite, eventually you're going to reach a point where you're going to terminate and you're going to get a set of yellow vertices. And again, if we have, say, for argument's sake, we can't continue onto another blue set of blue neighbors there because then we can just indefinitely carry this process through, and it will never terminate. Alright, so we may assume that, like all these vertices, again, their blue neighbors terminate to that single one. And you cannot go and do a recoloring. You can't go and place your you can't go and color those vertices blue there. And say color the vertices there yellow, because what is going to be the problem in that case? The problem there again is going to be here, there. Okay, the blue vertices are adjacent to that single blue vertex there, so that coloring is not going to work there. Alright, so what is the implication of that? You're going to find this alternate yellow-blue alternating path. Right, so you're going to find, like say, an edge there, and this path is going to carry on and on until it reaches that last set there, and you're going to find a alternating chain, yellow-blue alternating chain. Okay. Now the thing is, you can do this for any two colors. You can do it for green and red. You can do it for purple and red. You can do it for purple and blue, and so on and so forth. Any combination of two colors within this vertex neighborhood. Okay. So what happens now? How can we use this? All right, so basically you get these disjoint alternating color path chains. As an example there you get one between those two colors, between those two colors there, between those two colors, and between those two colors, right? Right, and so there we've got another path, alternating chain. And there as an example, we've got the purple-red alternating chain as well. Now, if we look at, say, the green and the yellow, and we know there exists an alternating green-yellow path, then where's this path going to go? Right, so I mean this path could, right, it can't escape there without crossing some of the edges, right? So there it's going to get to the yellow, it's going to have to cross an edge. And that's going to be a problem because the graph G is planar. You can draw the graph in such a way that none of the edges cross. So that's going to be a problem. So these alternating color chains are going to cause a problem. So what is the moral of the story? It means that there exist two colors in the open neighborhood of V where you can get away with not finding such an alternating color chain. So essentially it means you can color this graph using the required 5 colors. So there's going to be a point where it's going to break down and you're going to be able to eliminate such an because that's where the problem comes in. It comes when you have an alternating color, a path that alternates between two colors. So we can find two colors in the open neighborhood of V such that no such alternating chain exists. So hence you can color the graph with the required amount of colors. Right, so again, that's where the problematic case comes in. It becomes with that alternating color chain. So basically, what's going to happen is you're going to get a crossing somewhere. So therefore, you're going to get a situation where there are two colors for which no such alternating chain exists. So you can color the open neighborhood of V. You can color instead of having the 5 colors, you can color two of the two vertices in the open neighborhood of V. You can color them with the same color because we just proved that there are 2 vertices for which there exists no alternating path. Right, so that completes the proof. So you can always color a planar graph with 5 colors. You can get away with it. And remember, they actually showed that you can do better than 5. You can actually use 4. Right, so going back to the textbook, there's a section on outer planar graphs and minors of graphs. I'm going to leave the section on minors for you to read through on your own. The section on outer planar graphs as well, I'm going to leave that for you as self-study. Okay, so there they just give us a characterization, a definition of an outer planar graph, and for the condition that needs to hold for a graph to be outer planar. So there's a little characterization for outer planar graphs. And there again, just some results on outer planar graphs. Again, they look at the size of an outer planar graph. It's at most 2n minus 3. And that brings us to that last section on the Hamiltonian planar graphs. Again, a graph is Hamiltonian if it has a Hamiltonian cycle. Hamiltonian cycle is a cycle that contains all the vertices of the graph. Right, so that brings us to Grinberg's theorem. If G is a Hamiltonian planar graph of order n with a Hamiltonian cycle C, and if you look at a planar embedding of G, Remember we said an edge of G not lying on a cycle, the cycle itself, that is a chord of G. Now note that every chord and every region of G lies either interior to C or exterior to C. So if you look at all the regions of G, those regions either lie inside of the cycle or they lie outside of the cycle. So what they have is they define two quantities. They define quantity Ri and Ri prime. Now Ri denotes the number of regions interior to the cycle C, whose boundary contains exactly I edges, and Ri prime is the number of regions that are exterior to C, and the boundary contains exactly I edges. Now here's a nice little example of a Hamiltonian planar graph. The edges colored with bold black, those are the edges on the Hamiltonian cycle. And as an example, here you've got a region interior to C, okay, and there you've got a region exterior to C. Right, so here they've got quantities. They've got the quantities R3 is the same as R3 prime is 1. So there's that region is an R3 region, and it lies inside of the cycle, and that's also an R3 region which lies outside of the cycle. So both R3 and R3 prime are both equals to 1. If you look at R4, that is the one that you've counted. That's the other one that you're counting. That is the other one that you're counting, right? So those three regions are on four edges, and they lie inside of the cycle. And if you look at R4 prime is 2 because it's this region here, okay, and it is that region there. Right, then if you look at this last one here, R5 is equal to R7 prime is equal to 1. Okay, why is that? So where's R5? There is an R5 which lies inside of the cycle. That's 1. There aren't any others. And then R7 is 1. R7 is 1. Now where is R7? Right, so R7 is the boundary of the exterior region. So it's basically this region here with these edges, right? All right, okay. So it's basically that whole region there. And there is exactly